Beacon Labs runs two AI systems on the same clinical data. One flags patients at risk of an adverse event. The other writes summaries of trial protocols. From the outside, they look like the same thing, but their regulators treat them like two completely different animals, and one word explains why. This is Amazon Web Services AI Practitioner Prep from Stack Lessons. On with it. By the end of this video, you'll be able to draw the nesting hierarchy from memory and say exactly what separates a supervised classifier from a generative model. This vocabulary comes up throughout the course, so getting it precise now pays off everywhere. In episode 1, we established that this is a scenario exam. It rarely asks what a service does. It drops you into a business situation and asks which system you'd choose. We also met Beacon Labs, a 280-person clinical trial analytics firm working under HIPAA and GDPR, already running a retrieval augmented generation assistant and a fine-tuned writer on Amazon Bedrock. Today, we build the vocabulary that all of that rests on. Before we get into the mechanics, let's pin down 3 terms you'll hear throughout this video. A model is decision logic that was learned from historical data, not rules a developer typed out by hand. Deep learning is machine learning built from multi-layer neural networks that discover their own features from raw data. And generative AI is deep learning whose output is new content rather than a label from a fixed set of options. We'll also see Agentic AI come up later in this episode. We covered its full definition back in episode 1. So here's Beacon's puzzle in detail. System A is a SageMaker classifier that reads a patient record and flags adverse event risk. System B is a Bedrock generator that takes a clinical trial protocol and writes a summary. From the outside, they look alike. Both are AI, both touch sensitive clinical data, but the regulators demand completely different evidence from each one. And the reason isn't bureaucratic. It's structural. It comes straight from where each system sits in the hierarchy we're about to draw. Picture 4 circles nested inside each other. The outermost circle is artificial intelligence, any system that mimics human intelligence. Inside it sits a smaller circle, machine learning, covering only the systems that learn their logic from data. Inside machine learning is deep learning, the systems built from multi-layer neural networks. And in the very center sits generative AI, the deep learning systems whose output is new content. The rule is simple. A point can only be in an inner circle if it's already inside every circle around it. This picture is the whole episode. If you can redraw these 4 circles in 10 seconds, you own the vocabulary. Here's the mistake people make constantly. They use the words AI and machine learning as if they mean the same thing. They don't. Every machine learning system is AI, but not every AI system is machine learning. A rule-based expert system that follows thresholds a human wrote is absolutely AI. It just lives in the outer circle because nothing was learned from data. The nested picture makes this impossible to confuse. Machine learning is a smaller circle sitting inside AI, never the same size. Amazon Web Services puts it cleanly. Machine learning is a type of artificial intelligence that performs data analysis tasks without explicit instructions. Notice the phrase that carries all the weight there, without explicit instructions. That's the line between machine learning and everything else in the outer circle. Nobody handwrote the logic. The system worked it out from the data. Think about the direction the logic flows. In classical programming, the developer writes every rule by hand. Rules and data go in, and answers come out. You can read that logic line by line. Machine learning flips it. The developer supplies the data and the known answers, and the training process discovers the rules for you. Those discovered rules are the model. So classical programming is a recipe you write, while machine learning is a taste test. You hand it thousands of dishes and their ratings, and it figures out the recipe on its own. So this gives us a precise definition of a model. A model is decision logic that was learned from historical data, not rules a human typed out. It's an artifact that came out of training, holding its knowledge in adjustable mathematical parameters. And because the logic emerged rather than being written, it can generalize to patterns nobody explicitly described. That's its power, and also exactly why regulators want to look inside it. Bring that back to Beacon Labs. Their adverse event model emerged from thousands of historical patient records with known outcomes. It can now score a brand new patient no engineer ever described. That's exactly why regulators treat it the way they do. They'll ask what data it was trained on, which features it relies on, and how its error rates vary across demographic subgroups. SageMaker Clarify exists to answer precisely those questions: bias detection and feature importance for a model whose logic was learned, not written. Quick checkpoint before we go deeper. AI is the outer circle. Machine learning is the learns from data circle sitting inside it. A model is that learned logic, and it's what regulators audit. Now let's step one circle further in and see what makes deep learning special. Amazon Web Services defines it this way. Deep learning is an artificial intelligence method that teaches computers to process data in a way inspired by the human brain. That brain inspiration points at the defining feature: layers. Deep learning stacks many layers of artificial neurons, and the depth of those layers is where all the capability comes from. Every neural network has three kinds of layer. The input layer receives the raw data. Here, the clinical node is plain text. Then come the hidden layers where the real work happens. Picture a radiology department where an X-ray passes through increasingly specialized reviewers. The first spots word boundaries, the next recognizes clinical terms, and a later one identifies risk signals. Each reviewer builds on the one before. Finally, the output layer produces the results, a risk score of 0.87. No single layer understands the whole note from scratch. Each just refines what the previous layer handed it. Here's the part worth pausing on. Nobody handed that network a list of medical terms to watch for. The hidden layers discovered which patterns mattered on their own during training. That's automatic feature extraction, and it's why deep learning dominates unstructured data like text, images, and audio. With classical machine learning, engineers would spend thousands of hours crafting features by hand and still miss patterns they never thought to look for. Deep learning finds them for you. Deep learning is a subset of machine learning, not the whole thing. Classical algorithms like random forests, gradient boosting, and logistic regression are machine learning, and they sit outside the deep learning circle entirely. On structured tabular data with a limited number of examples, they often beat deep learning outright. So Beacon's adverse event classifier, trained on neat tabular rows of demographics and lab values, might not need deep learning at all, and that's a perfectly sound engineering choice. Deep learning's real edge is unstructured data at scale: images, audio, raw text. Now we reach the innermost circle. Amazon Web Services defines it like this. Generative AI is a type of AI that can create new content and ideas, including conversations, stories, images, videos, and music. Focus on those two words: create new. That's the whole distinction. A generative model doesn't pick from a menu of existing answers. It produces something that didn't exist before. Put Beacon's two systems side by side, because this is the sharpest line on the whole exam. The SageMaker classifier takes a patient record and outputs a risk score of 0.87, labeled high. It's picking from a fixed set of classes, and you grade it on precision, recall, and F1. The Bedrock generator takes a protocol document plus a prompt and produces a multi-paragraph summary that never existed before. It samples from a distribution over the entire vocabulary, so you can't grade it against an answer key. You evaluate it for things like hallucination and factual accuracy. One discriminates among existing categories. The other creates. Here's the way to lock it in. A classifier is a multiple choice grader. Hand it an answer sheet, and it picks A, B, C, or D from options that already exist. A generative model is an essayist. Give it a prompt, and it composes a fresh answer using the patterns it absorbed during training. The grader can only choose what's already on the page. The essayist can write text that has never existed before. That single difference drives different metrics, different failure modes, and different regulatory postures. The generator beacon uses a foundation model, and it lives inside the generative AI circle. Foundation models are trained by a third party on internet-scale data, with parameters numbering in the billions. They learn through self-supervision, so no labeled dataset is required. On Bedrock, Beacon accesses the model through an API and never owns the weights, which changes everything about how they can audit it. And because these models are general purpose, you adapt them by prompting or fine-tuning rather than training from scratch. One more term the exam expects you to define: Agentic AI. An agent autonomously plans and executes multi-step tasks, invoking tools and APIs along the way, without a human prompt driving each step. Contrasts that with a plain generative model. You prompt it once, it answers once, and it's done. An agent receives a goal, breaks it into steps, decides which tools to call, calls them, checks the results, and adapts. We'll go deep on how agents actually work in the dedicated Agentic AI episode. For now, just hold the definition: autonomous, multi-step, tool using. So how does an agent connect to all those tools without a mountain of custom code? That's what the Model Context Protocol solves. The official documentation calls it an open source standard for connecting AI applications to external systems, and it compares it to a USB-C port for AI. Just as USB-C gives you one standard plug for every device, MCP gives an agent one standard way to reach any tool. Here's the problem MCP fixes. On the left, without a common standard, every agent needs a custom connector to every tool. 2 agents and 2 tools already means 4 bespoke integrations, and it explodes as you add more. That's the N times M problem. On the right, with MCP in the middle, each agent implements the standard once, and each tool implements it once. Now you're at N plus M connections instead of N times M. Amazon Bedrock Agents implements the same pattern on Amazon Web Services, giving agents structured access to APIs and data stores. And one clarification the exam likes: MCP is an open standard, not an Amazon Web Services invention, and not a model itself. Now we can answer the opening puzzle. The SageMaker classifier is a supervised machine learning model that outputs a label. Beacon trained it on their own labeled data. They own the weights, and they audit it feature by feature with SageMaker Clarify. Its failure modes are false positives and false negatives, both measurable with standard metrics. The Bedrock generator is a third-party foundation model that outputs new text. It was trained on vast unlabeled data Beacon never saw. They don't own the weights, and its failure modes are hallucination and factual drift. That's why the regulators' questions are completely different, and it all traces back to where each system sits in the circles. Let's lock in what to carry forward. AI contains machine learning, which contains deep learning, which contains generative AI, nested, never equal. AI is not the same as machine learning because rule-based systems are AI with no learning at all. A model is learned decision logic, not handwritten rules. A classifier predicts a label from a fixed set, while generative AI creates new content. An agentic AI acts autonomously across multiple steps, with MCP standardizing how it connects to tools. If you can redraw those 4 circles from memory, you're ready. Now let's see how well you absorbed all of this with a quick 5-question quiz. All right, time to put your knowledge to the test. Question 1. A hospital deploys a constraint solver that follows thresholds hand-coded by clinicians to schedule operating rooms. No component learns from data. How should the system be classified within the AI hierarchy? Option A, it's artificial intelligence, but not machine learning, because its logic was written by humans. Option B, it's machine learning because it makes automated decisions. Option C, it's deep learning because it processes structured data. Or option D, it's generative AI because it produces a schedule. Run the decision rule from earlier before you answer. The right call here is A. Machine learning requires that the logic be learned from data. This solver's thresholds were written by humans, so it lives in the outer AI circle only. It's AI, but never machine learning, deep learning, or generative AI. Question 2. Beacon Labs needs to evaluate two systems. System A outputs an adverse event risk score from a fixed set of classes. System B produces a multi-paragraph protocol summary. Which evaluation approach fits each one? Option A. Both are graded with precision, recall, and F1. Option B. System A is checked for hallucination, while System B uses precision and recall. Option C. Both are evaluated only through human review. Or Option D. System A uses precision and recall, while System B is evaluated for hallucination and factual accuracy. Lock in your answer before I give it away. It has to be D. Here's why. System A is a classifier that outputs a label, so classification metrics like precision and recall apply. System B generates new content, so you evaluate it for hallucination and factual accuracy. Different output types, different evaluation frameworks. Question 3. A data engineer claims that because a model performs well on structured tabular data with only a few thousand rows, it must be a deep learning model. Why is that reasoning flawed? Option A, deep learning can't process structured data at all. Option B, classical machine learning algorithms like random forests and gradient boosting are machine learning but not deep learning, and often outperform deep learning on small tabular datasets. Option C, all machine learning models are by definition deep learning models. Or option D, tabular data can only be processed by generative AI. Think about which circle these algorithms stored in. This one is B. Not all machine learning is deep learning. Random forests, gradient boosting, and logistic regression are machine learning that sits outside the deep learning circle. And on small structured tabular datasets, they frequently beat deep learning outright. Question 4. Beacon Labs wants a system that reads a new trial report, queries a regulations knowledge base, cross-references trial criteria, and drafts a compliance summary, deciding each step on its own. Which term best describes this? And what standardizes its tool connections? Option A, a supervised classifier standardized by SageMaker Clarify. Option B, a single-turn generative model standardized by prompt engineering. Option C, Agentic AI with the model context protocol standardizing its tool connections. Or option D, a foundation model standardized by token-based pricing. Got your pick? Let's see. If you said C, well done. A system that autonomously plans and executes multi-step tasks by invoking tools is Agentic AI. And the model context protocol is the open standard that standardizes how agents connect to those tools and APIs. Question 5, and this one is a callback to an earlier episode. Beacon Labs needs its assistant to reference clinical trial protocol documents that change every week without retraining the model each time. Which approach fits? Option A, retrieval augmented generation, which retrieves fresh documents at query time. Option B, fine-tuning, which retrains the model on the new documents weekly. Option C, distillation, which compresses the model into a smaller version. Or option D, prompt caching, which stores repeated prompt prefixes. Pause here if you want more time. The answer is A. Retrieval augmented generation pulls fresh documents at query time, so the model can reference facts it was never trained on with no retraining required. That's exactly why it fits Beacon's weekly updating protocol documents, as we covered in episode 1. And we're done with AI. Machine learning, deep learning, and generative AI, the nesting hierarchy. If this earned a spot in your study routine, hit subscribe so the rest of the Amazon Web Services AI Practitioner prep finds you automatically. The comments are where I learn what's working, so tell me what landed and what didn't. Got a certification on your list I haven't covered yet? Drop it below. That's how the next course gets chosen. And if the style or the speed could be better for you, I genuinely want that feedback. Catch you next time.